Welcome to this webinar session on large open space protection. In this session, we will look into the fire detection strategies in large open spaces with emphasis placed on smoke detection. We will start with the environmental and operational conditions that characterize the large open space and review common fire detection strategies deployed in these spaces. We will then close off outlining design options for aspirated and optical beam smoke detectors in large open spaces. Large open spaces have become a key design feature in commercial and public buildings, serving many purposes, such as enhancing aesthetics, facilitating natural ventilation, acting as reservoirs to collect smoke, providing for the efficient storage in the form of vertical storage. Examples of building designs incorporating large open space include atriums, transport hubs, stadiums, industrial plants, and of course, warehouses. Large open spaces come in different shapes and sizes. However, the two most common traits are large volumes and high ceilings. They can be open to the outside to facilitate natural ventilation, or can be air conditioned, giving rise to cross flows. Because they are tall structures, vertical thermal gradients are expected from internal operations or solar loading. Having high ceilings, certain sections of the large open space will be hard to reach, especially sections close to the ceiling. The objectives of a fire detection system in a large open space is to detect fires and provide notification for the safe evacuation of occupants. The signal from the fire detection system might also initiate the activation of other fire subsystems, for example, smoke control to purge hot gases from the space and avoid thermal damage to the building structure. Risk-informed designs could also be implemented in the selection and deployment of fire systems to protect building assets or limit the impact of a fire on the operational and economic activity in the space. When selecting a fire detection system in a large open space, you must ensure the technology is suitable for the environment. For example, because of thermal layering, ceiling-mounted systems must be able to withstand high and fluctuating temperatures and airborne pollutants in the case the structure is open to the outside. Fire detection systems must provide timely notification to a fire event, operate reliably, and have a low total cost of ownership throughout their operational life. Common detection strategies deployed in large open spaces are air sampling smoke detection, optical beam smoke detection, spot type smoke detection, sprinklers and by default heat type detection, video-based smoke detection. Aspirated smoke detectors comprise sensitive chambers and provide for an integrated smoke reading from smoke entering multiple sampling holes. Because of their flexible pipe layouts, the detector units can be mounted at floor level for easy access, whereas to detect stratified smoke, pipe runs must be required on multiple levels, adding to the installation cost. Optical beam smoke detectors provide integrated smoke reading along their beam path. They are relatively easy to install and have a low cost of installation and maintenance. They can, however, be susceptible to nuisance alarms and faults, particularly for single wavelength type detectors from changing operational and environmental conditions. Spot detectors provide point addressability, which is desirable to identify the point of fire origin, however, are capable only of localized detection. Accessing spot detectors for maintenance and service can sometimes be a difficult and expensive exercise. Sprinklers rely on the temperature of the smoke layer to activate and provide the means to control or suppress a fire. Since they rely on the heat signature of the fire, sprinklers in high ceiling installations might not respond to small energy fires. Emerging video smoke technology provides fast detection as well as visual verification of a rising smoke plume. However, repeatability of the system can be severely affected by color of the smoke, color of the background, lighting conditions, and airflow. Now for some theory on how a smoke plume will develop in a large open space. The fundamental fact of a rising smoke plume is that it entrains air, which will dilute the smoke concentration and cool down the plume. During its ascent, the smoke plume might reach thermal equilibrium with the ambient air and stratify at a level below the ceiling. This will be the case for small energy fires or where thermal barriers exist near the ceiling. The plume can spread laterally from the action of cross flows and not reach the ceiling, or the plume can have sufficient lift to reach the ceiling, albeit delayed and with reduced smoke concentration. The development of a smoke plume in a large open space can be complicated and potentially affect the performance and reliability of ceiling-mounted fire detection systems. These three schematics show the projection of the smoke plume on a ceiling that has spots, aspirated, and optical beam smoke detectors. The spot-type smoke detector will see and report smoke only at a single location. With the aspirated detector, smoke will enter multiple sampling holes. This is called cumulative sampling. The optical beam smoke detector will measure the smoke over the entire beam path. Both aspirated and optical beam technologies will integrate the smoke reading over a region rather than at one point, making them inherently more sensitive to dispersed and low-density smoke than spot-type detectors, as will be the case of a smoke plume reaching the ceiling in a large open space. The benefits of technologies able to integrate smoke reading over a region were demonstrated in a BRE project, the results of which have influenced changes to the FIA Code of Practice on aspirated smoke detection. This chart is derived from internal computational fluid dynamic modeling and helps visualize and quantify the detection performance of the three smoke detection technologies mentioned earlier: spots, aspirated beams, as well as sprinklers in a large open space. All systems were ceiling mounted in an 8-meter high ceiling space, and the model fire was a T-square medium without an incipient stage. The fuel soot yield was set to 1%, which represents the burning characteristics of cardboard. As can be seen, a detection technology with sensitive settings and one that integrates the smoke, the case of aspirated smoke detection, can provide timely notification to a fire event, which in turn can allow actions to be taken while the fire size is still manageable. Now let's consider different design options for applying aspirated smoke detection in a large open space. In this example, the large open space is represented by a warehouse with high rack storage. It should be noted that these are generic guidelines, and for specifics on sampling hole sensitivity and spacing, as well as height limitations, you will need to consult your local installation codes and standards. We start with ceiling detection, where the ASD system will provide an integrated smoke reading due to the cumulative sampling effect. In cases where storage racks extend close to the ceiling and form compartments, ceiling sampling points should be positioned above the aisles. Where a high risk for stratification has been identified or there's a requirement to detect small fires, the aspirated smoke detection pipe network can be engineered to provide 3D volume protection, such as drop pipes or capillaries from the ceiling or separate horizontal pipe runs with sampling ports at lower heights. Another option is by arranging sampling locations along the perimeter of the outer space. For this option, consideration should be given to the extent the stratified smoke layer will disperse horizontally. Also, consideration must be given to the presence of airflows from mechanical natural ventilation, and the provision of sampling across return air grills might be necessary. ASD systems that support extensive pipe lengths can have the end of the pipe runs extended to floor level, where smoke transfer time tests can be carried out, by a remote test maintenance point. Finally, at locations close to the detector, inline pipe components can be inserted for the conditioning of the sampled air before it enters the detector. These can include particulate filters, water traps, preheating. For optical smoke beam detector designs in large open spaces, we start with ceiling detection, where the optical beam will integrate the smoke signal along the beam path. Where smoke cannot reach the ceiling, intermediate horizontal beam detection at sufficient spacing between beams is a good solution to detect a rising smoke plume. Finally, based on preliminary computational fluid dynamics modeling results from a Fire Industry Association program, strategically deployed angled beams can provide more cost-effective detection of stratified smoke than intermediate horizontal beams. The spacing of angled beams must take into account the maximum horizontal spread of the stratified smoke layer, and angled beams should be crisscrossed throughout the space. As concluding remarks, large open spaces present unique challenges to smoke detection systems because of high smoke dilution, the potential of smoke not reaching the ceiling, and access difficulties to systems for service and maintenance. A solid understanding of large open space built environment is required to ensure detection systems are designed and deployed to detect smoke plumes that are diluted, stratified, or deflected from cross flows. Aspirated smoke detection is a proven approach that addresses the challenges in large open spaces. Beam detectors are also another option, but do not offer early fire warning capabilities compared to aspirated smoke detection.